So, we hear all the time about how AI finds patterns in data, right? But have you ever really stopped to wonder how it thinks? How it actually reasons its way through a problem, kind of like a detective solving a case? Well, let's get into it.
That is the big question. We're going to go way beyond just spotting patterns today. We're going to see how an AI, what we call an agent, can use pure, cold, hard logic to navigate a world it knows absolutely nothing about and make some pretty high stakes decisions.
Okay, to really get this, we need a peek inside the agent's mind. And it's really built on two core ideas. First up, there's the knowledge base. The best way to think about this is like the agent's own personal library or its memory. It's just a growing list of every single thing the agent knows for a fact is true about its world. It starts off empty, but it's a quick learner. And second, you've got inference. Now this is the agent's superpower, for real. This is the engine of logic that takes all the facts it already has and deduces brand new ones, conclusions that weren't there before. This is where the real reasoning happens.
So theory is great, but how do we see this in action? Well, let's throw a simple AI agent into a classic challenge. Welcome to the Wumpus world.
We're going to follow our heroic little agent on its quest. The mission sounds simple. Go into a dark cave, find the gold, and get out. The catch? That cave is packed with deadly hazards. And the number one danger is the terrifying Wumpus. It's a monster that will gobble up anyone who dares to enter its room. So yeah, our agent's job is to find that shiny gold while staying very, very far away from this guy. Now, the agent can't see anything, but it can perceive the square it's in. So if it's next to the Wumpus, it smells a terrible stench. If it's next to a bottomless pit, it feels a breeze. And if it finds the gold, it'll see a glitter right where it's standing. Oh, and one more thing. It has one arrow. Just one, so it has to be absolutely sure before it shoots. These simple rules are the only clues it has to work with. So here's our game board. Our agent starts right there in the corner, at square 1-1. At this moment, its knowledge base is pretty much empty. The rest of the cave? A total mystery. Let's watch how our agent uses its knowledge base and that power of inference to figure out its very first moves. So, right at the start, in square 1-1, the agent perceives nothing. Zip. No stench, no breeze. So boom. The very first fact gets logged into its knowledge base. Square 1-1 is safe. It marks it okay. Because it knows its starting square is safe, it also knows it can safely move to an adjacent one. So it makes a choice and moves over to square 2-1. And the moment it enters square 2-1, it perceives something new. It feels a breeze. This new fact immediately gets added to its knowledge base. Okay, so this is the crucial moment. What can the agent figure out now? It's standing in 2-1, and it feels a breeze. What does that logically tell it? This is where that inference engine just kicks into high gear. Step 1, the agent knows the rule. A breeze means a pit is in an adjacent square. Okay, so a pit must be in one of the squares touching 2-1. Step 2, it checks its knowledge base, and it knows for a fact that square 1-1 is safe. Step 3, using simple process of elimination, it deduces a brand new piece of knowledge. There has to be a pit in either square 2-2 or square 3-1. And that is just a perfect example of how powerful this is. The agent doesn't know exactly where the pit is yet, but by using pure logic, it has successfully identified where the danger is. It has literally created new knowledge out of thin air. Now, this whole reasoning process, it isn't just a clever guess. It's all happening inside the agent's brain using a formal mathematical language. And that language is called propositional logic. It sounds complicated, but really, it's just a super precise system for writing down facts as sentences that can only be true or false. And it comes with very strict rules about how you can combine them to find new truths. This table right here basically shows you how the agent's thoughts translate into this formal language. See that first symbol for not? That's how the agent stored the fact there is not a pit in 1-1. And its final deduction, that there's a pit in 2-2 or 3-1, is written using that or symbol. The entire thought process, if there's a breeze in 2-1, then that implies a pit in one of the adjacent squares, is captured perfectly by these simple symbols.
Okay, so an agent can avoid a digital monster in a cave. That's cool, but why does any of this matter in the real world? It matters because the Wumpus world, as simple as it looks, forces an AI to do the three core tasks of any intelligent system. First, represent facts about the world, like there's a breeze here. Second, use inference to create new knowledge from those facts, like so there must be a pit nearby. And third, use that new knowledge to decide what to do next, like I am not going to step into those squares.
And that's really the key thing to take away from all this. The exact same logical cycle is what allows an AI to do incredibly complex things. It's how a medical AI can help a doctor diagnose a rare disease by logically connecting symptoms from millions of patient files. It's how a logistics system can plan the best route for thousands of delivery trucks, navigating traffic and weather changes on the fly. The scale is unbelievably different, but the logical foundation, it's the same.
So it leaves us with this really fascinating thought, doesn't it? If this very basic, rigorous, true or false logic can solve a deadly puzzle in a digital cave, just imagine what kind of incredibly complex problems it could help us solve out here in our own world.